Speaking of reliability, a podcast with good friends talking with you about reliability engineering topics.
Welcome to Speaking of Reliability. This is Kirk Gray.
And this is Fred Schenkberg. Hey, Kirk.
Hey, Fred. Good to talk to you again.
Yeah, it's been a little while, so I wanted to chat with you because I just the other day got a question that may well end up being a whole series of conversations because it's just way too much fun in this one.
Okay.
The gist of the question that I think would make a good individual podcast was, what are the failure mechanisms that moisture contributes to? I'd say, causes or, is a part of or does whatever. And and the question started as, why do I need different chambers? Can't I just do this in the thermal chamber we have? And I said, well, what's your product? And it says, well, it's our first one going outside. And one of the engineers is concerned about rain and humidity and stuff like that. And I said, okay, does your thermal chamber have rain and humidity in it? And I go, no. Well, it's really hard to stress your product with moisture in a dry chamber. But then it became more, well, what do I need to worry about with moisture? And I'm like, really? At least you're asking, which is great. It's like, and I started rattling off all these different things, and I haven't heard from them. I think I probably scared them off, off the idea of even doing testing because it's going to fail.
Yeah, you put a matrix up of 10 by 10, right?
Oh, easy.
If moisture causes corrosion.
Yeah.
Okay.
And that's a whole field all in itself.
Right.
We could go on and on just about corrosion.
Right. And that would be related to temperature, how fast the corrosion occurs, how
even if there's a
exposure.
current, current could cause, or even a voltage field could help, which is one of my favorite kinds of corrosion is the dendritic growth. Right. Beautiful little images of those things.
Little stalagmite and stalactites. Yeah.
Yeah. I saw a picture. It was a factory that made one of these artificial sweeteners. I don't remember which brand it was and stuff. And I was walking up on the dock, and they had I don't know what it was doing, but it was scavenging some of the moisture from some room that had this sweetener in it. So it wasn't just water. It was like sweetened water, and it was dripping onto concrete. And when I saw it, it had plowed a hole through this poured concrete with rebar, because you could see the rebar.
Yeah.
That was 3 inches in diameter and a foot deep.
Yeah.
And I asked, how long's that been doing that? And he goes, about 2 years since we had repaved it.
Oh boy!
Oh my God! It was some acidic thing. It must have been in that moisture. And I'm like, do I really want to go into this factory?
Yeah. Well, that Florida condominium in Florida was 14 stories or something. Mm-hmm. I think the rebar was corroded. I mean, it got in there because it's near the ocean. Yeah. And especially with salt water, it's even more corrosive. And I think that's what caused that building to collapse.
Yeah, no, it lost a lot of strength in some of its main supports. Yeah.
So corrosion
in and of itself, moisture by itself can do it, but then you add contaminants, it'll be bad.
Right. It causes oxidation. It causes fretting, corrosion in your connectors.
Oh, yeah.
It accelerates that. And that's a very difficult mechanism to identify easily.
Yeah.
So,
the Grand Canyon, though, it's done some really cool stuff, that corrosion. It's not corrosion, that's wear. That's a whole different thing, isn't it? It's wear.
The magic of the water molecule is when it gets to 0 degrees, it expands. I mean, the ice forms and expands. And that's what, of course, like you say, the Grand Canyon, that was runoff, but also.
But it splits rocks. It'll split granite.
Right. It split rocks. It reduces things. So, right. But my experience is a lot of contamination. It activates and makes it corrosive. When it's added. When I put a 95, 85 in the humidity chamber, like I talked about the DIMM modules that used to plug in your computer motherboard to add and subtract memory.
Yeah.
I could almost guarantee if I put it in the chamber, I would get loss of memory, some memory cells, because those contacts would be contaminated because they didn't clean them that well sometimes.
Or then stay clean because you're in a. I had that happen it was two places. One was Seoul, Korea, just from air pollution.
Right.
And the morning humidity in, condensation that would occur on electronics. It was full of sulfuric acid essentially. And then in another place was in a clay modeling room for an auto manufacturer, where they do the big full size clay models of stuff. That clay contained a large amount of sulfur. And so it was in the air and it just ate computers. It just ate them.
Yeah.
And it was just a little bit of moisture. It was the humidity coming off the clay. And they kept it humid in there to keep the clay malleable and pliable and soft and all the other stuff.
Right.
But that poor workstation that was sitting next to him was just getting eaten alive. But corrosion in so many forms, moisture either does it itself or enables it.
Right. And this is where also moisture, it really requires for it to be, for the mechanisms to be active or to be able to see them, requires time and usually some other energy to drive it. You can't just, I'd say that person that was making the outdoor equipment's going outdoors, obviously the first thing is to seal it up, make sure it's, the internal parts can't be exposed,
not
to
the direct rain and stuff. And it's really difficult to hermetically seal something.
Well, you have to worry about cooling it too at the same time, so that airflow, when you do hermetically seal, it means it's not going to be cooled by airflow through
that's
the
a whole different failure set of mechanisms. But the idea is that most things outdoors, I'm thinking in telecommunications and automobiles and everything else, is the concept that your product will have no moisture because you put an O-ring around it is nonsense. It'll keep direct rain at bay at best, but the humidity will become the same. whatever that word.
Yeah. Eventually. Well,
it'll balance out inside and outside. Eventually, the air is the moisture and the air and all of the other things are going to diffuse through whatever you have. And
everything leaks.
Everything
leaks. Right. So eventually you are going to get some of that moisture in there. So then it's going to, freeze. So you might actually, if moisture got in between some component and in a crack and freeze, it might actually open
the lead right off. Yeah.
Yeah, it might to continue to expand a crack, just like it would in a rock. And
so ice is one of it. The other side is boiling steam. One of the things that I learned early on in my career with electronics is a phenomena called popcorning. And it's a descriptive term to what it actually does. It doesn't turn into a nice white fluffy edible thing, but this little IC chip will have too much moisture in it, and its construction is sensitive, and it goes through a reflow oven, which is at 220 C or something like that.
Well, it's a ramp of 200. It's like a 100 degrees C. It's very fast when it goes to the IR reflow. So it's right, and so the moisture absorbed in the package suddenly is turned to steam. So it will explode. It'll pop.
Essentially, it'll just make a small crack. And what's insidious about it is that it just creates an opening, and the chip will still work unless it's really a bad break. But typically, it'll just work fine. And it's almost invisible. It's just a very, very small hairline crack, usually around the leads or on the surface or on the edge. And then
it takes some moisture to seep in there.
Yeah, not a lot. It takes only about a week for it to occur.
Right.
And then you got a little bit of voltage and current, and you got the recipe of our imperfect air that we breathe day in and day out.
Right.
It will fail. The corrosion.
Right. But in that case, it's again, it takes some time. It's a time function with the chemical reaction of, unlike a mechanical break or something that happens during vibration, which was kind of instant, usually, at some level.
Yeah, at some level.
You have to usually expose it. Like my idea would be, I think moisture would be best used, and we always the standard 85 degrees C, 85% relative humidity test.
Would you
It's
do you know where that 85 came from? What its history is?
no. Do you?
Yeah, I
Okay.
did.
Tell
I
me.
dug into it, a whole pile of it.
Okay.
Yeah. Oh, I'm drawing a complete blank on his name at the moment. There's two guys that they were working. The original test was at Motorola, and
Okay.
they were doing experiments with the plastic encapsulated components, because up until that time, diodes and resistors and everything else were in little steel
Right.
cans,
Right.
and or ceramic. But they were going, well, we want to make this less expensive. How about we use this epoxy thing?
Right.
And they were having a lot of trouble with the epoxy bonding to the platform that the leads were on, and so they had lead frames coming out of it, and they needed it to bond around that metal and create a tight seal to keep moisture out of the internal, other than just the normal humidity that comes and goes, but pretty much anything that could carry chlorine atoms in there, like enough moisture or humidity that there's enough of an opening that you get contaminants in it.
Right.
And so what they found was that if they used 85, and it was because their humidity temperature chamber, that was the most it could do. And it is very difficult to get higher than that with humidity, because the more higher temperature, the more moisture the air can contain, and it's really hard to maintain a 90, 95. Unless you're in Houston, then it just seems to be natural.
Just open the doors.
Yeah.
Anyway.
And so they found that if you do that for a week, it'll identify and power the unit, power the chips. That if there is a break, the corrosion will manifest itself and you can detect it. Right. And if not, then you assume that you got a good seal. And they did a bunch of cross sections and a bunch of other stuff, all the right stuff to do that. And then they kind of made it a standard test. And then it got built into standards that you do 85 in your electronics to look for this not dendritic growth, this breaks or lack of sealing on your chips. Well, it became so popular, and there were so many chambers out there that people just started putting everything in 85 and assuming, to my chagrin, assuming that if it passed that for a week or a month, that it meant something. And I'm like, well, what failure mechanism are you dealing with? Which brought me back to this question: is that if you don't know what you're looking for, you're never going to find it,
Or you don't know what the physics are behind it. Like, for instance, okay, you just talked about moisture intrusion into a package or the lead frames.
Right.
And of course, we know that the epoxies used in plastic encapsulated microcircuits are highly proprietary because of the matching of the TCE between the lead frame and the epoxy, and how the heating and cooling of that chip is going to expand and contract internally. And you want to make sure that seal around the metal to plastic never breaks, right? I mean, obviously, that's what you're forming. So it's they've had to adjust, and they add things to that epoxy to make sure that rate of expansion and contraction is very close to what the metal frame and the chip and all the other things are. So there's not, because that has led to significant delamination problems in the certain kinds of sections.
And that's where popcorning, the steaming, is similar in how it actually causes the corrosion, but it's different in how the crack forms. And so 85, after you potentially popcorn a bunch of stuff, would allow you to detect it. And you're talking about it takes time. One of my clients years ago had a product that was like a Fitbit, but different kind of thing. And they were, before I got on board with them, they had used it's on your wrist. Watches are on your wrist. Let's use the Swiss watch moisture standard test. And I was like, well, what does that do? And he said, well, you take the watch and you put it in 3 feet of water. Mm-hmm. And if you're doing a 1 meter moisture resistant or waterproof thing, and you pull it back out, well, how long do you wait? Well, you just dip it in and then pull it back out, shake off the water. And as the watch is still working, you're good. And I'm like, they use these, steel cans that are welded basically. And the chance of moisture getting into a Swiss watch is pretty low. And even if the under the bezel or under the glass is full of water, but as long as it's still ticking, it passes that test. And I'm like, well, that is not terribly useful. Well, they had a little power port on their wrist device that was just a standard USB, mini USB port. And there is not sealed. It was not epoxied. It wasn't watertight in any form or shape. And so they went and tested, 20 or 30 of these things. They dipped it in water, shook it off, looked at it, they were able to read it. It still worked. They were happy. So then they set those samples aside and went off to do the other things they're doing. They dropped them, they stretched them, they stepped on them. They did all kinds of cool stuff. And a week later, they went back to those samples because they thought, we could use those samples again. They're good. And every single one of them had failed due to corrosion. It took a week for that corrosion at room temperature to manifest itself. So meanwhile, they shipped 70,000 of these.
Yep. And there they go.
And they all failed within a week or two.
Right.
So corrosion, we could, like I said when we started, we could do on that one all day long. And you mentioned ice, which is a physical pressure of moisture on stuff.
Mechanical.
There's mechanical. There's a wear feature of moisture. If moisture is running, if water is moving, and like on an impeller, what's the name of that mechanism? If the impeller isn't working designed well and spun at the right at the right rate. Cavitation.
Cavitation, where it's
it creates a small vacuum or a bubble, basically, when that bubble collapses, that it hits the surface with an immense amount of force. And it chips away at whatever that material is. And so cavitation is one that's kind of an odd one. You got to really know that it exists.
But you said particles in moisture, some kind of, can actually do physical wear too.
Oh, just water by itself can do wear.
Add
a few boulders, it does wear a lot faster.
But So there's moisture in itself by itself.
It's a solvent.
Well, it is, but what actually people don't realize is absolute pure water, distilled water, is can actually etch circuits. I mean, it can actually, it's slightly acidic, I think, because we would, in an ion implanter, we would run absolutely 15 mega ohm water between 200,000 volts and ground, and it, was in polyflow tubes, and if it was any contamination, of course, it wouldn't be 15 mega ohms and you'd have a short. But when it spilled, if we ever accidentally unscrewed one of the hose lines,
which you wouldn't know anything about.
Actually would leak, if you were trying to empty one or change a filter or something, and you get a little bit of leakage of water, and it would drop on a printed circuit board. It would etch the circuits. It would actually etch a trace and cause failure later.
Even tap water or drinking water or just water from a creek, it is a solvent. It takes apart other things. It disassociates other molecules really, really well. That's why we wash our dishes with water. It does a good job at doing that, dissolving things.
Adding a few salt ions in there, you get some really conductive water.
Well, that's generally really pure water is not terribly conductive. You add a little bit of ion, chlorine and bromine and all the other stuff that's even just on our fingers.
Like I say, 20,000, 200,000 volts between 3 feet of polytubing and ground. It's very, very resistive. It's 15 mega ohm per centimeter, I think.
Wow.
That's incredibly resistive.
Yeah.
People don't realize it, but there's very rare cases of pure.
You have to really work hard to get it.
Oh, we had super filters on those lines. I mean, it was absolutely.
You're not just pulling it in from the creek.
No way.
So what else? I mean, one we didn't talk about, especially outdoor applications, is, I've seen standards for driving rain or pouring, hard rain or stuff like that.
Right.
I also saw one it was a solar panel company, and they were testing hailstones, and they had
They fired a gun.
Yeah, they had little
guns.
They had little brass forms that they would make perfect sphere ice at a certain pressure, and there was some standard that was like a hailstone was always perfect, and I'm like, really?
Yeah,
but it was reproducible for him, that it was this much mass and this hardness and stuff like that. And then they just use this gun and then just blast through everything.
Right. And I just always wonder if they, if they go to destruct. I mean, they just increase the hailstone size, or
the one I saw, there wasn't anything left. It just shattered this whole panel.
Okay.
Absolutely shattered it.
So they go beyond and to destruct. Okay.
Oh, and it was a golf ball sized piece, which luckily is not that common, but you can have that on your roof and you get hit by 200,000 golf balls. Yeah, it's going to break.
Oh, well, we've had that kind of thing. Right. And I don't know. In fact, solar energy is very popular around here, and rooftop solar. But I didn't, I always wonder. We had to replace our roof just a few years ago because of a really bad hailstorm that terribly damaged our cars and things. But I didn't hear a whole lot about the solar panels. I assume
they've gotten smarter with the upper coatings they put on it, so that it's not rubber-ish, but it can take a good impact without fracture. But there is one of them that was made to look. Their solar panels were made to look like fluorescent tubes, and they were blown glass.
Yeah.
You could walk past them, they'd break. You didn't need any ice, and stuff like that. They're not in business anymore. So, but what else can moisture do? Dig a little deeper here, Kirk. We got a couple minutes left here.
Let's see. Moisture. I guess it just is a additive to so many things, like corrosion actually eating into mechanical physical structure, like a frame, weakens it so that the strength of the material it's not. I'm trying to think of. Of course, buildings, we talk about the corrosion.
Well, I used to make, one of my first jobs coming out of the military was at a factory. We made anodes, essentially. Yeah. They would take on the charge as a sacrifice to protect the piers, the rebar within the pier structures. So that these anode devices, these cables, essentially with this cool plastic on it, would be buried in with the rebar, and it was a sacrificial piece that would extend the life of the rebar within the piers, and saltwater piers usually.
Yeah,
it was, but it was a way to combat it, because the moisture is going to get in your concrete. No doubt about it, and then it's going to eat the rebar, and so it was a way to say, hey, this is more tasty. Come over here.
Stay away from that area.
Okay. I mean, as we're recording this, there's, I think, Hilton or Milton. Milton is a hurricane head towards Florida. Yeah. Hopefully everything works out with that. It sounds like it's going to be a big storm. But wave surge and just it's a part of erosion. But when you have flooding and all the contaminants and all the debris it picks up, hopefully you're not designing products that have to withstand that. But if and are not expected to withstand that. But if you're on a ship or on a boat, just the salt spray and all of the forces that waves can produce is amazing.
Right. But we design cars to withstand all kinds of weather conditions, and we don't design them to be put underwater, which
never very long anyway, not at all.
Asheville, yeah, it happened recently in Asheville. That just pretty much ruins the car. It makes all kinds of, we call them latent defects in it that you won't find for a while.
Oh, that's another one that moisture encourages is fungus. Think of all the drywall that had to be pulled out and all the molds and funguses that'll grow if you don't get your stuff dry. That's another whole, it's more in the building environments, but I've run into fungus inside components or inside electronics where it was in a moist, damp environment and this kind of creepy looking black mold was growing in there and shorting stuff out.
I haven't hit that. I haven't seen that yet.
Yeah.
So.
I
don't know where. No,
that was in Brazil is where the products were being used. It was out in the jungle, I guess, but humidity also, erodes a lot of fabrics. I remember folks that when I was in the Army, they were looking forward to getting stationed in Hawaii and it's the vacation spot. And they would get island fever with about 3 weeks. Well, we've been to all the beaches. Now what do we do? We're going to be here for 3 years. Yeah. But they found that anything leather or fabric based was seriously degraded by the humidity.
Really?
Yeah. And it would just fall apart. And so all kinds of stuff would just deteriorate, and it was humidity. And I don't remember what the mechanism was. But it basically acting like a solvent is the way I understood it. And it deteriorate threads and fabrics and so on. But funguses and molds were a common problem because of the humidity. It encouraged those things to move forward.
Well, that's one thing great about living at 5,000 feet. We have a lot less humidity, but that actually is a problem for like when we brought anybody bringing wooden furniture that's glued together.
Because it just shrinks. Well, that's another one. Yeah, Kirk, that's another moisture related one. Is the lack of moisture.
The lack of moisture, then suddenly something shrinks.
Yeah.
Right. So you were talking about the problem of popcorning where the component has absorbed moisture. Up here, it's helpful, but it also is a negative in electronic manufacturing in the fact that our air is drier. And so that creates more static, more ESD issues.
Ah, that's true. The lack of moisture.
Right. They actually would pump in humidity into storage techs. We had an assembly line, board pick and place and all that, but they would pump moisture into the big production area to help reduce ESD down.
Yeah, keep things conductive so that it dissipated.
Right, exactly. So, plus ionizer air things and stuff like that. So moisture can have a benefit in manufacturing as far as reliability, not too much. And then you also have to worry about condensation when you're doing testing with moisture.
Yep.
Somebody said, this thermal chamber has, humidity capabilities. But obviously, if you take it down low enough in temperature that you're going to get condensation, and that's not really valid.
Well, it depends on what you're trying to do. If you're going to be outdoors and it's going to see condensation, then it's perfect. And if you're inside a computer lab that's not going to see condensation, then, that's not a good thing.
Not a good thing. And that's an invalid failure if you get standing water on your circuit board. So, that's something to be careful about testing moisture. But in general, for the most things moisture it does take some time duration as opposed to accumulative fatigue that you can create with vibration very quickly, or rapid thermal cycling, which also helps, swing the temperature. Most of the moisture issues are going to be, I think, over time, generally more over time than.
And the corrosion's the biggest one, and that was our first one, and that typically takes time to do it. Well, anyway, so we ran into, I didn't keep track here. I should have maybe 5 or 6 big areas of types of things to consider. The bottom line, though, is moisture is not just an outdoor problem, and it's everywhere. Right. And in any design, it is something to at least address or think through is how it's going to interact with your product. And Could be in your production facility, could be in the outdoor environment it's getting. It could be a slow-moving type of corrosion that takes years to manifest, or it could be one freeze-thaw cycle takes your component apart. Your part's completely apart. It is so multifaceted. And temperature along with moisture, it can really wreak havoc. And you know what's funny, Kirk, is that you can do all the moisture and water testing and everything else you want in your world, and you're controlling temperature and you're controlling, there's no vibration, there's nothing else going on.
Right.
Mother Nature does it all at once. She's very gifted at doing multiple stresses all the time.
Yeah, it's just like when people do swept sign, I said, where does that exist in nature?
That's right.
It's like, okay, yeah, the perfect sine wave. Anyway, yeah, you're right. So just, be aware of all the aspects that moisture can interfere and cause latent defects. And really is its main thing is it's very difficult to detect.
Unless you're looking for it.
Unless you're looking for it.
Look for it.
And yet special signals and, detection systems.
So anyway, it's one of those that, Kirk and I kind of just picked up on this one and started riffing on it, and we may have missed one or two mechanisms. If you know of another unique way that moisture can cause havoc with our products and systems, let us know. Head over to accendoreliability.com/go/SOR. A couple of ways to get in touch with us there. Kirk and I and the other hosts of the show are available through LinkedIn and our About pages. And like this question, and we didn't even start on the vibration one, which was another topic there. So that might be another topic another day. But if you've got a question like this, where you're curious of, what are these stresses or mechanisms or some other aspect of reliability engineering work that we do, let us know. And we'd love to chat about it and get you an answer as quick as we can. But with that, I'm afraid to go take a shower. I might dissolve.
Well, you're just so sweet, Fred. Whatever. You're made of sugar. You'd be like the Wicked Witch. Anyway, we'll do this again soon.
All right. Thanks, Kirk. Talk to you later.
Talk to you later.
Cheers.
Bye.
Thanks for listening to Speaking of Reliability. We invite you to join the conversation. If you have a question or a topic that you think we should discuss in a future show, please let us know. You can find a comment box below the episode show notes, or just leave a note as part of a review on iTunes.